Okay, question number 4 of the 2019 AP Calculus exam. This was also on the BC exam. I have not read the question yet. I'm solving this in real time, so hopefully I get it all correct. A cylindrical barrel with diameter of 2 feet collects rainwater as shown in the figure above. The water drains out through a valve in the bottom of the barrel. The rate of change in the height of the water of the barrel is modeled by this function. So I'm going to make a note that dH dt is negative 1/10 root h. That's a fairly clean function, easy to differentiate or integrate. H is measured in feet, T is measured in seconds, so I can make a note there. H is feet, T equals seconds. The volume of a cylinder, oh, they gave you the formula for the volume of a cylinder. That is nice. They don't usually do that. They don't usually do that. Now, if it was a cone, they typically give you things that are cones or spheres or pyramids or something like that. Anyway, find the rate of change of the volume of the water with respect to time. So we're looking for dV dt. So find the rate of change of the volume with respect to time when the height is 4 at h equals 4. So I'm going to need to find the derivative of that volume. This is a related rates question, and it looks like it might be a full-on related rates. They have not done this. Oh, and they squeezed your differential equation in part C? Blah! Okay, interesting. Okay, so anyway, so they haven't done a full-on related rates question in a while, so I guess they were due for one. I did not predict this. So the derivative is 2r dr dt times h plus r squared dh dt. And dv dt at time h equals 4, that's going to be pi. Did I miss something? Oh, the radius is constant. Ah, dadgummit. Okay, I kicked into autopilot, wasn't thinking. This is a cylinder that is filling with water. The only thing changing is the height. My radius is a constant 1 in this, so I'm going to undo what I just did. Geez, I'm sorry. That's what happens when I do this live. All right, so my volume is now going to be, instead of pi r squared h, my volume is just going to be pi 1 squared h, which is just pi h. Oh, that's sexy. Okay, that's much nicer. Okay, so let's undo this. Bad work. I'm just going to cross it out to save time, because on the AP exam, you don't want to waste time erasing. So my dV dt is just going to be pi dH dt, which would be, do I have dH dt? Negative 1/10 h. Okay, so that's going to be pi times negative 1/10 square root of h, and then at h equals 4. So that's going to be pi times, I need to indicate that I'm plugging in 4. So then dV dt such that h is equal to 4 would be pi times negative 1/10 times the square root of 4. Normally I don't simplify, but that's pretty easy. Square root of 4 is 2. 2/10 is 1/5, so that's going to be negative pi over 5. Always include units. Volume over time. We found dV dt. Volume would be feet cubed, and my unit of time is seconds. I'm going to make that 5 look more 5-ish. There. All right. Question B. When the height is 3, is the rate of change of the height of the water with respect to time increasing or decreasing? So we want to know if something is increasing or decreasing. We need to know if that thing's derivative is positive or negative. So we want to know, is dH dt increasing or is it decreasing? dH dt increases when its derivative, the second derivative, is positive. dH dt will decrease when its derivative, which is the second derivative of h, is negative. So we will need to find the second derivative of h. So dH dt is negative 1/10 root t. So the second derivative is going to be, I'm just going to ignore the negative 1/10. The derivative of root h is 1 over 2 root h, but this is this will be implicit. I have to then multiply by dH dt, and I know that dH dt is negative 1/10 root h. So this is going to be negative 1 over 20 root h times, this is interesting, negative 1/10 root h, and the root h's cancel, and we are left with just 1 over 200. There was nowhere to plug h equals 3. I got a positive value, therefore dh dt is increasing because the second derivative is positive. Always. There was nowhere to plug in the 3, which makes me wonder if I did this correctly, so I'm going to double check this. We are looking for, is the rate of change of the height with respect to time increasing or decreasing? And so if that thing, so we need the second derivative. My first derivative is negative 1/10 root h, so the derivative of that is that times dh dt, which is another. Yeah, I think I did all that right. So I just wasn't, I was not expecting all h's to go away, so I was a little bit hesitant as I was working that problem, but I think it's good. Okay, at time 0, the height of the water is 5 feet. So my height at time 0 equals 5. Use separation of variables to find an expression for h in terms of t. So we are now going to solve the differential equation, and that was very nice of them to say use separation of variables, because you should, in a perfect world, know that this would require separation of variables even if they had not indicated. But there's my function, or my derivative. I will separate that. And so dh over root h would be negative 1/10 dt. I think I'll go ahead and make this h to the negative 1/2 dh. I'll go ahead and do the antiderivative of this side. That would be negative t over 10 plus a c. We'll add 1 and divide. That's going to be 2 square root of h for the antiderivative of that. Make sure I add 1/2 to it. Yep. Is equal to negative t over 10 plus c. And we need to now solve for the c and the h. I think I'll go ahead and solve for c. So I'm going to go up here. H of 0 equals 5, which means that 2 square root of 5 would equal negative 0 over 10 plus c. So c is 2 square root of 5, which means that my differential equation, 2 root h, is equal to negative t over 10 plus 2 square root of 5. We'll solve for h. Divide everything by 2, so negative t over 20 plus root 5, and then we will square both sides, and h is all of negative t over 20 plus square root of 5 squared. There's your answer, and we are done.